Thank you for being so awesome and putting up with all those videos. I'm really sorry, but I really appreciate it. This 1 out of 5, I do not recommend this. Whatever this is, it's terrible. It just keeps going and going and going. But we've got a test on Thursday. Okay, so let's see here. Can I think straight? Oh yeah, here we go. So I brought printouts, finally. I remembered. Formula sheets, tables, they're the same as what's posted on Moodle. So the formula sheet and the tables, we've only used the Z table so far, so I only brought the Z table. I'll bring the T table when we're ready for it, but that's not until later. Okay, so on the test, I'll bring fresh printouts. Otherwise, I'd have to check them all, and that's annoying. And so, but don't worry, if they're clean, I'll reuse them and spend a lot of time erasing after tests. So we'll reuse them. Don't worry about the trees too much. And so those are yours to keep and to study from, and just to have and to hold. And so, and then I'll bring fresh versions for the test. Okay, let's see here. So today, I just want to run through the format of the test, what to expect in terms of grade distribution, and then I'm open to questions if you have any, although I know it's a busy time for other tests, so you might have that breathing down your neck. All right, let's see here. Where are we? So I did post the practice for test 1 as well as the solutions. 18 pages, are you nuts? Yes, I am, I guess. This, I call it practice for test 1 because I want to give you an overview. Obviously, I'm not going to have a test like this, but there are lots of different things that we can be doing. And so, hello. Let's see here. I don't know. Settings, who knows? Oh, what was I saying? Oh yeah, so there's lots of different practice here, just to give you an overview of all the things. And I did mention in my announcement yesterday that I don't have a video on question 6, so it's not going to be on the test, obviously. You're welcome to try it, it's kind of fun, but it's not tested, it's not something that we've introduced, and so just ignore that one. And then I didn't realize it, but when I had a look at the solutions, I guess I had an outline. This is old, so, but we're gonna be sticking to it fairly closely, but I'll do a fresh outline for the test, but that's kind of it's gonna be similar. Okay, let's see here. Oh, and before we start, we meant to go through, sorry, the Poisson distribution. I don't want to spend time on it in class, so what I'm going to do is I'm going to post a bonus assignment, and so it'll include a video and you answer questions. It's a bonus assignment because you don't have to do it, but if you do it and you get a better grade on that assignment than the previous assignment, or maybe a future assignment, then I'll just drop your lowest assignment. Okay, so if you decide not to do it, that's totally fine. It'll get dropped because it'll be your lowest. But if you do it, it's a way to kind of recoup some assignment marks. Okay, and so it's just a different distribution, kind of fun, but not something I want to spend time on in class because today is more important. Okay. All right. Nothing to it but to do it. So test number 1. There's a little bit of multiple choice and a multiple choice short answer. Chapter 1, remember chapter 1, we introduced the different types of variables. We introduced sampling techniques, all that kind of the basics. And so we're gonna have multiple choice for chapter 1 questions and for five marks. So I want to give you the breakdown so that you know where to expect the marks. Now, how I write my tests is I do them chronologically. So the questions will be in the order that we saw them in class. I find that that's a little bit helpful just to kind of nudge you in the right direction of what am I supposed to do here? Right? And so, because that's always hard. Chapter 2, what did we do in chapter 2? We introduced numerical summaries. We talked about shapes and center and spread of distributions. When should we use the median? When should we use the mean? That kind of thing. And so still kind of multiple choice with some short answers. What's the short answer, do you think? Well, we did the 5 number summaries and we had to find some outliers. And that's the little, you have to do the calculation to find the lower and the upper bound. So it's not truly multiple choice, but kind of. And that's for 5 marks. Sorry, I haven't written in a long time. It's like I was on summer break, except in a fever state. Still warm though, right? So sweaty. From chapter 3, we'll start getting into probability. Maybe it's just my least favorite part. Probabilities. Oh, what's the probability of seeing a whale, a dolphin, blah, blah, blah. But chapter 3, there's going to be a table question. So I give you the table of information, right? Counts or probabilities, and you're able to answer those kind of just quick 1-mark questions, right? On the assignments, what's everyone's favorite one? If the male has blue eyes, what's the probability that the female has blue eyes, right? That one's always tricky, right? Very similar to that, right? Now, I will say on the assignments, the wording is quite subtle, can be very difficult to decipher. Now, it's still going to feel that way on the test, but I am going to make sure that it's very clear, right? And so, or at least as clear as I can be. Okay. Tests feel harder because it's the first time you're reading the question and you're under pressure and you haven't seen this before. But test questions are always simpler than assignment questions. So for chapter 3, we're gonna do 5 marks for a table. Oh my gosh. A table type question. All right, so I give you the table, information, and then what's the harder one? A tree. All right, conditional probabilities with a tree. And so for 4 marks, hey, you're on easy street now. Oops. 4 marks is a tree. Thinking about your assignment questions, what's a tree type question? Yeah, and, what did you do? There's the voting one. There's the HIV one. That's tricky. I would argue that the HIV one is probably the hardest one, right? Because you have to think about what does it mean for a test to be accurate, right? You don't have HIV, then an accurate result would be no, right? Whereas if you do have HIV, then an accurate result would be yes, right? So you have to kind of think about that. Obviously, I'm not going to do that on the test, but you've seen it now. And so I guess it's fair game. But I'm thinking more in terms of the voting one, which I think I even put on the practice just for another version. What was the voting one? College degrees and such. I can't remember. Let's see here. What's another tree one that we did? Can't remember. Anyways, chapter 4. We didn't do all of chapter 4. I'm going to focus on the z-scores and the binomial, but I am going to break up chapter 4 into those 2 parts. And so for 5 marks, you've got the z-score questions. Something follows a normal distribution. As soon as you see that, right, you're going to think, probably a z-score question, right? Something follows a normal distribution with a mean this and a standard deviation of this. What's the probability of something less than this, something more than this being between these 2 things, right? And you've got lots of practice on that practice handout. What else could we do? We could work backwards, right? If the score, let's say, is 50, what's the probability that someone, I went forwards. I wanted to go backwards. If 60% scored higher than you, then what was your score? That's working backwards. Those 2 options. Then I'm going to have 4 plus 2 marks. Now I say 4 plus 2 because 4 of those marks are real and 2 of them are bonus. Score for the binomial. What's the bonus, do you think? It's going to be the normal approximation to the binomial. Now, hey, why isn't this? Maybe they need to be linked up. It's not letting me change my pen. We're stuck with blue, I guess. Anyways, that's a bummer. Two bonus marks. Wow, the total's not that high. 5 and 5 and 5 and 5 and 5 and 5 and 5. No. But close. 2 bonus marks can make a huge difference, right? And so this is on the normal approximation to the binomial. And you do have an assignment on it. I even posted an additional video just because it is kind of tricky. So you do have practice for it, right? And it's kind of a nice link between the normal distribution and the binomial, right? But whenever you find yourself in a binomial situation and you think, oh man, that's a lot of calculations, right? Then you can see if you can use the normal approximation to the binomial. Usually you can, and then it's a lot easier. Okay. All right. And then that's it. Hey, that doesn't look too bad, right? Oh, sorry. Any questions about the format? Yeah. You do have the whole class time. When you're done, you can just, well, you have to hand it in first and then you can leave. It's closed book, obviously. But that means the questions are easier. So nice. Any other questions? Yeah.
2 questions. So we're allowed to bring these formula sheets in?
I'll bring you fresh ones that you have to use. So those ones are yours. to do whatever you want
And
with.
chapter or assignment 8 and 9, those are the due to like on the day of the exam, but they are on.
They are on the exam. I just, yeah, gets weird with due dates, but they are on the exam. And one of them is the bonus question, so it's worthwhile. Cool. Any other questions? No? Don't look at me, Emily. Okay. Any questions you want to work through? No? Too painful to look at me up here?
Actually, I do have a question.
Yes.
From assignment 7, question 7.
Uh-huh. Let me see what we can do here. Assignment 7, you say? Oh, the normal distribution. Let's see, just in case there's some. Question 7? Aha. Okay. So I'm not going to test you on the empirical rule, but it is a good rule of thumb. Now, the empirical rule is mostly if you don't have a table, then you're still able to approximate probabilities, right? So we don't need to have a table. We could just answer everything with the 68, 95, 99.7 rule. But they become very approximate. Was there a part in particular, or do you want to run through?
Well, I got I guess the second one.
Yep.
Correct. But even if I looked at the solution, I still got it correct, even though I was off for a couple decimal points, and that was kind of similar to my other.
Oh.
And I got that one wrong, so that's why.
Do you think it's a coding thing in the background? Let's have a look. I'll just screenshot this. And let's see. I'll just do 1 or 2 and see. Oh, hey, yeah. Okay. I guess I need to restart that. Come on. I do need to be able to paste. Let's crop top this here. Let's say assignment 7. Oh, there. Okay, so let's see here. Where am I? So we've got a normal distribution for some television, TV, some people call it. The mean price is 1,400 and the standard deviation is 120, and it looks like they've already done the work for us, right? Moving out 1 standard deviation each time. Correct me if I'm wrong, but it looks like it to me. Okay, and so what does that mean? It means that between here and here, we've got 68% of the curve. Between here and here, we've got 95% of the curve. And between here and here, we've got 99.7%. If you're using a table, you would get even more precise values, right? And then if you're using Excel, you would get even more precise values, right? But the 68, 95, 99.7 rule is just what we use as a rule of thumb. And so what's the approximate percentage of buyers who paid more than 1640. More than 1640 is going to look like this. Right, you can answer this without the table that they give you, but it sure does help. 1640 here. Well, from the table, we know, or from the image, we know we have 95% here. By symmetry, I have 5% in the tails, but that's split evenly amongst the tails. So that means that I have 2.5% here and 2.5% here. So the probability, or what's the approximate percentage of buyers who paid more than 1640? Well, that's going to be this area, right? Because you've got the prices on the x-axis. And so the percentage should be 2.5. And like I said, if you're using the table, you would get a more precise value, but should be very, very close. Is that? Now let me go and cheat. Phew. I did it. 2.5. Okay. Let's see. Let's see. Maybe let's pick a different one. Let's do, how about the second, trying to pick one that's good. What's good? 1280. No, boring, boring, boring. How about the last one? Always leverage that symmetry, right? And so if we paid, let's see here. I'm just gonna copy this so that we have it. So we want to know what's the approximate percentage of buyers who paid between 1400 and 1760. So now what could you do? Think of these as puzzle pieces. And what you want to do is you want to find this area up to 1760. Now, knowing that 1760 is 3 standard deviations above the mean, what can we say? Well, then we can say that, well, the total area, if I move out 3 standard deviations on either side of the mean, is going to be 99.7. But by symmetry, I'm smushing that in half, right? By starting here at the mean, right? It's symmetric about the mean. So then this area here has to be 99.7 divided by 2, which who cares? No, we do care, I guess. Math. 99.7 divided by 2 is 49.85%. How could you check your work? Well, you know the total area is 1 underneath the curve, right? And so you would expect it to be close to 50%, but not quite 50%, right? Because symmetric about the mean, right? And so you're expecting from the mean all the way out to infinity, right? Technically, these tails go to infinity. They never, ever close. And so, but you're expecting this area to be less than 50%, but close to it because you've moved out 3 standard deviations above the mean. Nice. Does that? Yeah, nice. No problem. Any other questions? Yeah. No. I don't want to. Yes, I can. conditional probability. Two, 3, 4, and 5. You got it. I'll do this. There. Let's do this. Put it on a fresh page here. Conditional probability. I meant to change it. Swaziland's not called Swaziland anymore. But so that should be updated. Anyways. Okay. So 25.9% of the population has HIV. Sorry. Now, right, think about so whenever you see something kind of tricky like this, try a tree diagram. On the test, I'm going to say, make a tree diagram to guide you in that direction, right? And so often I'll do that. Tell me why this is appropriate. Oh, okay, sure. Right, and so I'll tell you to make a tree diagram, okay? And so, but in this case, we've got kind of two things, and we're given conditional probabilities. And always when we're given conditional probabilities, it's usually easier to solve with a tree. And so what we're going to do here is we're going to start with our first layer, okay, which is going to be someone either has HIV or they don't. And so I'm going to do, they either have HIV or they don't, right? Or maybe we can do the complement here. Use some notation that we're used to seeing. Okay. And so then I can do let H be HIV positive. And then what am I going to do? Gets confusing because it can be HIV positive and then have a positive or negative test. And so let P be a positive test. Maybe I should do, no, I'm going to stick with it. Gets confusing with the positive and positive. Okay, so we're told that 25.9%. Now I'm going to use the proportion because right in our math, we should be using the proportion. We have to use the proportion. And so it's just easier if we just boil it down to the proportion right away. And so we're given 0.259. It's the probability of having HIV, which means that the probability of not is 1 minus 0.259, which is 0.741. Notice that the branches, right, if they come from the same root, they have to add to 1. Okay, so we use that a lot. Now, what can happen? You can have HIV, you can test positive, you can test negative. You can not have HIV, you could test positive, you could test negative, right? Some of those are accurate, some of those are not, but they can all happen. And so the next phase in our tree here is this. Okay, so blah, 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 blah. If you have HIV, so conditional on having HIV, then the test is 99.7% accurate. Now, accurate would be a positive test, right? So here I'm going to do my branches P and not P. And then I'm going to do P and not P again, right? Now, conditional on having HIV, then the test is 0.997 accurate, 0.997. Okay. Which means, now, just be sure, 0.003 inaccurate. Let's see here. For those who do not carry HIV, the test is 92.6% accurate. Usually that happens because it's better to have someone who actually has it to test positive. It's better to catch that than to say, oh no, you're fine, right? That's better. And so there's often this trade-off, especially in medicine. And so if you don't have it, 92.6% accurate. Okay, I'm gonna highlight that because accurate in this case would mean not testing positive, right? And so here, this goes here at 0.926, which means, right, the probability of testing positive is 0.074. Oops, it's not very nice, is it? Okay. Now, for me, and this next part is a little bit overkill, okay, but I always like to just do it and then I have all my players in place, if that makes sense. And so what I do is I go down and I just list all the possible combinations, okay? And so here, I'll do the overkill in light blue. You don't have to do this part, but helps. HIV, testing positive, H, not positive, not H, testing positive, and then not H, not testing positive. Okay. Now, what we can do, right? This is the same, this is a sloppy version of saying H and P, right? H and not P, not H and P, right? So we've got these ands. Whenever you catch yourself saying and, you're multiplying probabilities, right? So to get to the combinations at the end of each of the trees, then you multiply down the branches. Okay? And so I'll just do it here on the sly. 0.259 times 0.997 is 0.258223. 0.259 times 0.003 is very small, 0.000. Mine gives scientific notation, it drives me nuts. 777, 1, 2, 3, 4, okay. And then 0.741 times 0.074 is 0.054834, and 0.741 times 0.926, I get 0.686166. It's tempting to do some rounding here, but I never do, because what's one of my checks that I can do? These all come from the same stem, so they have to add to 1, right? So that's one of the things that you can do to check your work. Equals 1. Yeah, let's assume. I'll come to check it, but looks pretty good. Okay. And so now I have all my players. Okay. And so what do we want to find? So that's why it's overkill, because I haven't even read the rest of the question yet. I know it's coming, but Right, I just like to have everything laid out, which can be time consuming, right? And so maybe on a test, see if you have time. If an individual from Swaziland has tested positive, what's the probability that he carries HIV? Now, the if is a subtle form of a conditional probability. So we know that they have tested positive. Okay. And so here, what are the ways that we can test positive? Well, we can test positive here, right? So here, this is positive, but also this is positive, right? You can have HIV and test positive, or, right? And whenever you catch yourself saying or, you're adding probabilities, right? And so, or you cannot have HIV and test positive, right? And so what we want to find is the probability of testing positive is having HIV and testing positive, or, I'll write or here, not having it and testing positive. We have those components already calculated, so we just have to jot those down. 0.258223 plus 0.054834. What is that? 0.258223 plus 0.054834. Now I can't really be trusted, well, ever, but definitely not right now. So if someone could confirm it, that would be great. 0.313057. You'll just take my word for it. Okay, so that's the probability of testing positive, right? Regardless of what your status is, okay? And so now we want to know, okay, so if someone is tested positive, what's the probability that they do have HIV? Now, what I'm going to do is I'm going to convert this into a probability statement. For me, that's the easiest way to deal with this beast. And so what I want to find the probability of H given that they tested positive. That's not easy to do, right? And so to take that sentence and convert it into a probability statement, that takes practice, right? But the more of these that you read, right, you'll start to see the pattern. What can I do now? From our formula sheet, let me grab it. Oh. Let's see here. I have conditional probability down here. So I'm gonna map these, right? Or if you just prefer to read it as the first one and the second one divided by the second one, that's what it is. That's what this formula is telling you, right? And so this becomes, so we want to find the probability of H given P is the probability of H and P divided by the probability of P. We have both of those components, right? And so probability of H and P is this HP, right? And so we have 0.258223 divided by 0.313057. Let's see here. 258,223 divided by that. because I've got a page break and I want to keep it on the same page. Just do it here. 0.82484333991. What's kind of a confusing part of this calculation? How did we get to the 0.3? Well, it was 0.258 plus the other version, right? And so that can be kind of confusing, but I've already used it. Doesn't that cancel to 1? No, it doesn't, right? Because you'd have to have a common factor, right? And so it does work out, but it is kind of confusing. I know that. Nice. Any questions about that one? Oh. Time is it? Oh, we've got lots of time. That's not what I wanted. How do I? There. Oh, weird. Let's read this one and convince ourselves that it's basically the same, right? It's not obvious, but it is basically the same question, right? And so Edison research gathered exit poll results from several sources, blah, blah, blah. Sorry. For Scott Walker. They found that 56% of the respondents voted in favor of Scott Walker, okay? Which means what? We know that the rest didn't, right? Additionally, they estimated that of those, that's a clue for a conditional probability, right? Which tells me, okay, I probably am going to use a tree here. Of those who did vote in favor of Scott Walker, 37% had a college degree, while 42% of those who voted against Scott Walker had a college degree. Okay. Suppose we randomly sampled a person who participated in the exit poll and found that he had a college degree, so we know that this person has a college degree, right? Or has tested positive. What's the probability that he voted in favor of Scott Walker? That's the same as what's the probability that they have HIV, right? So it's the same format, but it looks way different, right? I know that. So how are we going to build our tree here? First thing we're given, right? And how I decide my tree is, well, the conditional information is based off of whether they voted for Scott Walker or not. And so I'm going to let V be voted in favor. And I'm going to let C be a college degree. As long as you tell me what you're defining your variables as, you can use whatever you want, whatever makes sense to you, right? But notice how I'm always using a yes and a no version, right? Because it narrows things down. Okay, so they voted in favor or they didn't, right? You could have used another variable for the didn't vote in favor, but it makes it more complicated to look at. And then the conditional information that we have is, do they have a college degree or not? Okay. 56% voted in favor. 0.56, 1 minus 0.56 is 0.44. Okay. And then of those who voted in favor, 37% had a college degree, so 0.37, which means 1 minus 0.37 here, 0.63. %42 of those who voted against Scott Walker had a college degree. 0.42, 1 minus 0.42, 0.58. Overkill again, but it's just how I like to tackle these. I like to list the combinations down at the bottom. You see there.
Yes.
Hello. Siri, answer this problem. And go down, find each of these and probabilities. Let's see here. I'm gonna skip it because I feel like there might be other questions, but you can go through and do it. What are we trying to find here, right? Hardest part, arguably, is translating the question into a probability statement that you want to be solving for, okay? And so we want to find so you've randomly sampled a person and found that they have a college degree. So given that they have a college degree, what's the probability that they voted in favor? So you want to find the probability that they voted in favor given that they have a college degree. Applying the same conditional formula as before, this is the same as the probability of B and C, which you're going to find by multiplying down this branch, right? Divided by the probability of C. Now notice that there are two ways that we can have the C, right? And so here, the probability of C is the probability of BC plus the probability of not B and C. And that's it. So I'm skipping the calculator work, but hopefully that does it. Did it? What's the tree that I have on the, oh, I cheaped out and I used one of the assignment questions on the practice, didn't I? How about I'll post another, I have another one that I like. What could you have done? Do you remember the sock one? You've got a sock drawer. You could have done a tree for the socks, right? You draw your first sock and then you draw your second sock, right? And so should we do that? Or does anyone have a different one on this assignment? Let's see. Oh no. This one, I need to figure out a way to add that the rows are the males and the columns are the females, because that throws people off. But let's see here. I'm gonna screenshot. The socks will have to wait. I'll bring this in here. I'll do the first few, and then you'll see the pattern. Okay. First, I'm going to make a note that the males and then the females there. Okay. This is similar to the table one that's on the test, right? So it might be nice. You've got the totals. These are just the counts. Sometimes we use the proportions, but they behave the same way. Okay. And so blah, blah, blah. What's the probability that a randomly chosen male respondent or his partner has blue eyes? Okay. Now we can convert these into probability statements, which would look like what? It would look like we want to find the probability that the male has blue eyes. We'll use kind of hokey notation, or the female has blue eyes. This is the same from our probabilities, right? This is the same as the probability that the male has blue eyes plus the probability that the female has blue eyes, but then you have to subtract the overlap. This is overkill for this question, and I'll show you why. But this, subtract the probability that the male has blue eyes and the female has blue eyes. You could do that, right? All those counts are going to be out of 213 in this case, because that's the grand total. I'm not going to do that. I'm just going to use the counts, because I said the probabilities and the counts behave the same way, but this is where we get the formula from. And so what can you do? You've got males with blue eyes, there's 105 of them. And then females with blue eyes, there's 90 of them. So you could do 105 plus 90, but what's the problem? What's the problem? Counted this 59 twice, right? So you have to subtract that overlap. And so this becomes, or 105 plus 90 minus 59. 105 plus 90 minus 59 is 136. It wants the probability. Now the probability is out of 213, so it's going to be 136 out of 213. Yeah. So you can do it with the probability notation, but that takes a couple more steps, but you'd end up in the same location, or just using the counts and then dividing by 213, right? That's probably not the one that you were looking for. Probably the second one. It's the one I always get. What's the probability that a randomly chosen male respondent with blue eyes? Now, this is where I talk about subtle kind of wording, right? And so we know that whoever we've chosen is a male with blue eyes. So now we're given that the male has blue eyes. What's the probability that they have a partner with blue eyes? So we want to find the probability that the female has blue eyes, given that the male has blue eyes. You could use that, work through the probability of a female with blue eyes and a male with blue eyes divided by the probability that the male has blue eyes. Or what else could you do? Kind of make things easier on yourself. Well, now we know that the male has to have blue eyes, right? And so now the total isn't 213 anymore, because the total has changed to 105, because we know that, well, has to be out of these 105. How many of the females have blue eyes? And so here you're going to say, or 59 out of 105. So this makes your new total. And that's going to be your answer, 59 out of 1, whatever that is. So it changes what the total is out of, right? Because you've narrowed down your population. And then the rest of them are the same, right? Except now you have a male with brown eyes, so it narrows it down to the males with brown eyes. And what's the probability that the female has blue eyes, and so on and so forth. Is that? Yeah. Nice. Any other questions? 7. The socks. Ready for the socks? Okay. So for the socks, let's see here. Crop this up. I want to show you that you can use a tree if you want to, right? You can translate this into a tree. It's going to be kind of a big tree, so you might not want to. There's lots of different ways that you can solve this problem. Okay, but in our sock drawer, we have 4 blue, 6 gray, and 2 black socks in this case. You're going to grab 2 socks at random. Now, one thing that I will clarify is that you're allowed to assume that you pick out the first sock and then you pick out the second sock. Okay. And you want to find the probability that you end up wearing 2 blue socks. Okay. And so let's make this tree and see what it looks like. Oh, I'm going to need more space, aren't I? Okay. In the drawer, I have 3 different colors. And I've got blue, I've got, hey, and black. Come on. Gray. I can't even do BL or anything. BK. Black. I don't know. I try to avoid using 2 letters because it gets confusing. But I don't know how else to do it. That's kind of sneaky. All right. I have how many socks in my drawer total? I have 4 plus 6 plus 2, so I have 12 socks. What's the probability that my first sock is blue? The probability is 4 out of 12. Right, I have 4 to choose from, 4 blue ones out of a total of 12. So the probability of drawing a blue sock is 4 out of 12. My grays, I've got 6 out of 12. I'm going to keep that common denominator. You can use your calculator so you don't have to, but so I'm not going to reduce it is what I'm saying. And for the black socks, I've got 2 out of 12. Notice that again, this has to add to 1 because they stem from the same branch, right? Or from the same node, I guess, top, root, whatever. Okay, I've picked my first sock. Now I'm gonna go ahead, I'm gonna dive in again, and I'm gonna pick my second sock. How many socks do I have to choose from now? Now I have 11, right? And depending on conditional on what my first sock color was, that's going to impact the probability of the second sock color, right? And so this is why I needed a ton of space here, because I still have 3 socks. Uh-oh. Or 3 colors rather to choose from. Black, gray, or sorry, blue, gray, black, blue, gray, black. Hey, maybe I should use K instead. Right, because I don't like to use 2 letters. That's weird, I know. But it avoids using 2 letters for one thing. Blue, gray, black. Okay, so now my total's out of 11. If I pull the blue already, then I only have 3. 3 out of 11. I'll highlight this 11 here, right? But I still have 6 grays because I didn't pull a gray, and I still have 2 blacks because I pulled a blue. Right, on to the next branch. Now I pulled a gray, so that's going to impact definitely the counts of the grays for the second one, but I still have 4 out of 11 blue. I have 5 out of 11 gray, and I have 2 out of 11 black. So even though these are fractions, everyone hates fractions. You can convert them to decimals if you want, but they might be kind of nasty. Okay, for the last set of branches, I have 4 blue still out of 11. I have 6 gray, and I have 1 black. Now, for each of these, right, you can multiply down the branches to figure out which one satisfies what. And let's see here. I wonder if I can just copy this. So for part A, 2 blue socks. Will it copy? I didn't. Okay, that's okay. Don't worry. I'll sort this out. No, I won't. Okay. Copy. It's fine. Paste. So I do not want to make that again. So what you're going to do, just go through the tree. How many ways can you have 2 blue socks? Well, the first one has to be blue, and the second one has to be blue. So there's only one way that that can happen. And so the probability then is probability of 2 blue is 4 out of 12 times 3 out of 11. That one is okay, I think. Right. How about B? No gray socks. Paste that again. No gray socks. So it might be helpful if I put all the combinations down at the bottom here, but it would take a long, well, it's only 9 things, I guess, but no gray socks. That's going to be this branch or this branch or, we're off the hook. If I pick a gray sock first, then it doesn't qualify. So then I move on, or this branch or this branch, right? So you can find the probabilities at the end here and add them all up. Probability of no gray is the probability of B plus, gonna get lazy, BK plus KB plus KK. These should all have probabilities around them. Okay. So you could solve it that way, right? Just by visualizing all the different combinations. There are other ways. It's another way you could do it. Or if I do a slop for my first sock and a slop for my second sock, how many non-gray socks do I have to choose from initially? Well, 6 out of 12 were gray, right? So that means that I have 6 out of 12 that are not gray, right? And so here I have 6 out of 12 that are not gray, which means that if I've already pulled a not gray and the second one also has to be not gray, then I have 5 out of 11 left for not gray options. So you could do that as well, right? How about C? At least one black sock. Uh-oh. Okay. At least one black sock. We can talk about the ways that I can have at least one black sock. So that's 1 or 2 black socks, right? And so if my first one is blue, then the only way that I could have at least one black sock is if the second one is black. Right? Same thing, if my first one is gray, then the only way that I can have at least one black sock is if the second one is black. Now, if the first one is black, then I've satisfied the criteria of at least one. In fact, we have a couple of options here. So at least one, I'm in the clear, right? So it could be, the second one could be blue, that's still at least one. Second one could be gray, or I could have 2 black socks. That looks like a lot of calculations, right? In fact, whenever I see at least one, what I usually do is I flip it and I say, oh, I don't want to do at least one because that's 1 or 2, right? What if I just say, well, the total of these probabilities down here has to add to 1, right? So what if I just take away no black socks? You can find the probability of no black socks, right? And so you're going to find that they're the same. Now, if that doesn't come naturally to you, that's fine. You can do this. It's just more tedious. And often the way that we kind of arrive at quicker things is, I don't want to do that. That looks like a ton of work, right? And so here, or we can say the probability of at least one black is 1 minus the probability of no black socks. You can use the tree if you want, or those kind of sock 1, sock 2 slots. So I'm going to use that. So where the probability of no black socks is sock number 1 cannot be black. Now there were only 2 black ones out of 12, and so I have 10 out of 12 times the second black non-black sock. I have 9 out of 11. And then take that away from 1, right? And you'll find the same probabilities. That's the good and the bad part of all these probability questions. is that there are lots of different ways that we can approach it. Okay. And so see which way comes naturally to you and then practice that way. Don't do it my way just because that's how I do it. If you have a way that comes naturally to you and we get the same answer, you did it. Okay. And so here. Okay. What about, but just as a general rule, whenever I see at least, I often flip to the complement. I say, okay, I'm gonna find the opposite of that and subtract it from 1. Okay. A green sock. Wow. There are no green socks, so I'm gonna go with 0. All right, that's fine. What about matching socks? How many ways could you have matching socks? Oops. Where am I? C, D. I'll just say the probability of green is 0. E, the probability of matching is, well, I'll bring the tree in a bit here, but it's the probability of blue and blue, or, right, so adding the probability of gray and gray, or the probability of black and black. Visually, these are matching, these are matching, and these are matching. So whichever way you'd like to approach it. Now I'm curious, do you like this type of tree or the ones that we were doing before? I only ask because I put one of these types of trees on a test one time and I was not very popular afterwards. So, okay, now I know you like the ones before. We can do that. I like these. You can think about the total decreasing, but I'll do one from before. Like the HIV or the voting one, how about? Any other questions? Okay, I don't know. Hey, we did it. Good job, guys. We'll end there and I'll see you on Thursday. All right.